Good afternoon.
Good afternoon.
Good morning.
Good morning, afternoon, and good night all at once. So how's everyone today?
Oh,
We're
really
good. Yeah, we're good.
Good. All right, so let's see. Oh, I can't. Okay, there's Denon. I couldn't see you for a second. All right, look, so everybody's there at Mogollon, everyone's there at St. John's, and everyone's there at Winslow. All right, so did anybody do anything amazing over the weekend? And
We won our volleyball game, or our volleyball tournament.
nice. Was that at Mogollon High School?
No, it was in Florence.
In Florence, and you won it there, huh?
Yeah.
That's even more impressive than winning your own. Still
Yeah.
in somebody else's. So that's super cool. So what are you guys rated now? Where are
We've
you
been ranked one. Yeah, number one.
Nice, nice. So you're thinking back to back
Hopefully.
state championships?
Yes, hopefully.
That would be super cool. Anybody else? And beating Joseph City by 60 some points, that doesn't count. It's amazing. Well, I guess it is.
My soccer team and I beat Snowflake 1-0.
Nice. Very good. Very good. So do they have like a lot more players than you guys have?
Yeah, like a lot more. Like we only have like 4 or 5 subs, and they have like 2.5 strings. So.
Oh wow, that's pretty. Well, that's pretty amazing. That shows that you guys have worked on your conditioning. That's pretty awesome. Stay up with a fresh string of players. So congratulations. That is awesome. What else? Anybody else?
We beat Joe City.
Yeah, I know. I don't know if I told you, but I was out of town, and so I have a buddy of mine that was sending me like text updates, and I'm like, I wanted to just say, you know what, you can just stop right now because it's just making me depressed. So no, but I'm happy for you guys. That's pretty awesome. So just totally be overconfident. I don't even think you need to practice this week. You probably don't even need to do any plays or anything. Just tell the coach, just give us the week off. I think we got this next game coming up, right?
Yeah, that would be nice.
Yeah, tell them about it. So anyway, I actually walked by the Joseph City's head coach and one of their assistants yesterday, and all they were talking about was like everybody that was hurt. So you guys must have beat them up pretty bad. That's all I could say. So anyway, but anyway, it'll be fun. So all right, anything else?
So I had a bunch of family come up this weekend, and that was really fun. They went to the corn maze. We had some fires and a potluck dinner. We all just partied and played games, and it was fun.
That sounds like a great time. Well, are any of you into plays? Anybody into drama here? Yeah?
Yes.
Okay, so write this down. There's a one of the best plays I've ever seen in my life. It was called Wait Until Dark, and it's like a scary play. And I told my daughter about it for years because she's into the dramatic arts. And while we were in St. George, we happened to see a flyer for it. So I just bought tickets and we went, and it was fun. It wasn't as good as the production that I saw, but it was still, pretty good. So anyway, it's actually a scary, it's pretty intense. I would say it'd be like rated PG-13, like you wouldn't want little kids in the audience, but it is, I saw it on Halloween night and on a date, And I'm telling you, it was amazing. So anyway, Wait Until Dark. If you ever get a chance to see it, go see it. So anyway, anything else before we get started?
I have a cool story. There was a duck that got brought into an animal shelter and it didn't have a leg, and so the person who brought it in or whatever, they brought it to the robotics team, and the robotics team's gonna 3D print a leg for it so it can walk.
See, I thought this was another one of your jokes. I kept waiting for. He went into the vet's office, but the vet couldn't help him because the duck couldn't pay the bill, or something like that.
That's a good one. Maybe I'll use that.
Yeah, you can. Yeah, feel free to use that. But I was waiting. I seriously, it sounded like a good setup for a joke. But I actually would love to see pictures of this duck when you get it all. If you get a duck leg 3D printed and get it, working out, that would be super cool. So anyway. Yeah, that's awesome.
Mr. Strong, I could probably email you CAD files, those 3D files of the duck leg if you wanted.
Well, I want to see it walking. So take a video of it with your phone and then send it to me. I would love to see that. Anyway, that would be super cool. So, anything else? All right. Well, let's get busy then. We have just a little bit more to finish up on 3.6. We were actually in the middle of a practice problem, and I wanted to practice 7, and I just wanted to make sure that we were getting the right answer when we plug it in. Oh, I know what I was going to show you. I was going to show you a calculator trick on this one. Okay, so the question said find the slope of the line tangent to y equals cosine to the 5th x at the point where x is pi thirds. And so the reason for this was to, practice with the chain rule. And so we kind of rewrote this as cosine x to the 5th. And then when you take the derivative, you bring the 5 in front, cosine x to the 4th, times the derivative of the inside part, which is negative sine x. So you bring the negative sine x in front, and so you get that for the derivative. Then we plugged in pi thirds, and we get that. Okay? Now, the cool calculator trick is that do you remember I showed you that you could do derivatives with the calculator? Do you remember that? Did I show you that? I showed you that, right? No? Yes?
I don't think so.
Does that say?
Really? Man. Okay. Well, here's the thing. Here, let's go to the calculator here. All right. So under the math menu, okay, option 8 is in deriv. Okay. So under the math menu, the 8th option, you can take the derivative. So it pops up d, and then you put in the variable. So let's just say x, d dx, means you're taking the derivative. Inside the parentheses, you put in the function that you want to take the derivative of. And so the point is, what I was going to tell you is that your calculator can do this because the final answer is a decimal. Okay? If it just said take the derivative, you couldn't do it on this calculator. But because we're taking the derivative at a point, the calculator can do it where an answer is a number. Okay? So inside here, we're going to put in cosine to the 5th x. So another set of parentheses, and cosine x, and close off the x, close off the cosine, and then raised to the 5th. Okay? So I've got parentheses around the cosine x, and then the calculator puts its own around the argument, so this other set of parentheses. And then this is the key, is that, so your calculator knows the chain rule, it knows how to do it, and then you plug in the value. So where x is pi thirds, so we do second pi divided by 3. And then press enter. And there it is. Wait. Why are we getting a different answer? Let's see. I wonder. So negative 0.001. Let's see. Cosine x.
Are you in radians?
Yeah, I guess I better make sure, huh? Oh, rookie mistake. You have to be in radians. Thank you. Okay, so now we'll do it, and boom, there we go. Okay, so moral of the story, make sure you're in radian mode, because all of the rules, and we're actually going to talk about this, all of the rules for calculus and all the rules that are in your calculator are all assuming you're in radian mode. Okay? Is that like a Pikachu costume, or what is that?
I'm a kangaroo, so I'm a Joey with a Joey.
I got it. Okay. So, why are you dressed up today? Joey?
Sorry, what?
Why are you dressed up today?
It's homecoming week, and it's pajama day today. And
so how come the rest of you guys aren't?
Because they're lame.
Say no more. Oh, okay. All right. Got a little pajama action there. Okay. All right. So any questions on that or the calculator? So whenever you're taking the derivative at a specific point, you can use the calculator. That math 8. Okay? All right. Okay, it is important to remember that the trig formulas, why is that? Okay. That the trig formulas for the derivatives were obtained under the assumption that x is measured in radians. So, and the reason, see, the oscillation in degrees, it oscillates only pi divided by 180 in radians as it does in degrees. And so that changes the slopes, that changes the tangents, everything along the way. Okay? So, suppose that we wanted to find the trig value of a degree. Now, I show you this once and have you do a practice problem, but I'm going to just tell you right now, this is not going to be on a midterm or a final. Okay? You might be on a quiz, but that would be it. Because normally the idea is to change everything. Well, here we're actually going to change this to degrees. So what you do is if you have, to radians. If you have an angle that's in degrees, you multiply by pi over 180 so that the degrees cancel, and so now you're in radians. Okay? So then when you take the derivative, it's like you have to use the chain rule. So the chain rule would say the derivative of the sine is the cosine of pi x over 180 divided by the derivative of the inside part, which is pi over 180. Well, now you convert this angle back and say, okay, now pi over 180x radians is the same as x degrees, because now you multiply by 180 over pi to get rid of that. And so then that is x degrees times pi over 180. And so then we take, so our final answer then would be pi over 180 times cosine x. So when you take the derivative of a trig function that's in degrees, it's like, to put it back in degrees in the final answer, you're going to have to multiply by that conversion factor. Okay? All right. So see if you can do, I think the practice problem is the cosine of x degrees. All right, David, what did you get? What's the derivative of the cosine of x degrees?
Would it be negative pi over 180 sine x degrees?
Yep, that's it. So, because, see, when you convert pi over 180 to make it in radians, and then you convert it back, the difference is this multiplying by the pi over 180 because of the chain rule. Okay, so, and then the derivative of the cosine is negative sine. Okay. All right, good job. Any questions on that? All right, well, that's it for 3-6. So were there any other questions on 3-6? Oh, I think I did have a joke up here. Let's see if I can. Oh, yeah, so this is the joke. The question is, what is the chain rule? And you have to remember, I'm a Marvel nerd, right? So the answer is, whoever has the chain makes the rules. Okay, so anyway, you guys know who that is?
Ghost Rider.
That's Ghost Rider. Anyway. So, okay, don't go see the first Ghost Rider movie actually isn't bad. The second one, it's one of the worst movies ever. So don't see that. Okay, well, let's go on to 3-7. So 3-7 is on implicit differentiation. So could someone tell me, what does implicit mean?
Like explicit, like it says that, right? Implicit is like implied, right?
Right. Okay, so this is like implied differentiation. Okay, so differentiating implicitly. So functions can be defined different ways. So y equals blah, 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 that's where it's explicitly defined. It's spelled out. X equals a cosine t, y equals b sine t. That's called parametric, where a function is parametrically defined, which means it's the x and y are in terms of a third variable, t or theta. And then the third one is where the variable that you're taking the derivative with respect to y here, or with respect to x, is not solved for either variable. And so while there's a relationship between x and y, their relationship is implied. So we call that an implicit function. Okay. So explicit means spelled out. Like if you buy music and it says it's explicit lyrics, then that means it's spelled out. If they're talking about killing cops or sex or whatever, they'll just come out and say it. Okay? There's nothing implied. Right? Where when I was in high school, there was some pretty racy music, but it was more implied. I mean, it's kind of a lot of the same ideas, but it wasn't as, using the language or whatever. Okay? All right. So this is how an implicitly defined derivative works. So when we're going to, it's kind of like the chain rule in a way. That the idea is we're going to take the derivative of everything with respect to x. Okay? So on the left side, the derivative of y squared is 2y dy dx. Now you might say, well, why the dy dx? Well, it's kind of like the chain rule when I said, okay, when you take the derivative of blob squared, it's 2 blob times the derivative of blob. Well, the derivative of y squared is 2y times the derivative of y, which is dy dx. It's a little bit easier to write it like that. So instead of y prime, we usually will write it, the derivative as dy dx in this section. Now, so what about this? Well, so when we take the derivative of x, it's 1, but you can also put in there times dx dx. But see, you really don't have to, because the d over dx cancels to 1. Okay? But you could. And as a matter of fact, I would recommend that for the first few examples, until you get the hang of this implicit differentiation, that you write this in. Every time you take the derivative of a variable, any variable, you put times dy dx or times dx dx times dz dx, whatever it is. Okay? Now, so to find dy dx, so now the calculus is over. It's just algebra at this point, because now we're going to solve for this dy dx. And so to do that, we divide each side by 2y. And the dx dx already canceled, so we get dy dx equals 1 divided by 2y. So now this is different too, because whenever we've taken the derivative before, all of our answers were in terms of x. Well, no longer. Now we're going to have x's and y's in the final derivative answer. Okay? All right. So see if you can do the first practice problem there. All right, Nathan, what do you have?
dy dx equals 1 over 3y squared.
dy dx equals 1 over 3y squared. Excellent. Any questions? Anyone like me to go through that one? All right, great job. All right, an application of this is working with a circle. So it says the circle is not an explicit function, but it is an implicit function. So like if I have x squared plus y squared equals r squared, that's the standard form of the equation of the circle, centered at the origin with radius r. And so if I need to find the slope of a tangent of a circle, then I'm going to use implicit differentiation. Okay? So, for example, let's say I want to find the slope of the tangent of this circle at this point. Okay? So, first I find dy dx. The slope of the tangent is the derivative. So I say the derivative of x squared is 2x dx dx. The derivative of y squared is 2y dy dx. Okay? And now this is important. Over here I have a constant. The derivative of any constant is just going to be 0. So it doesn't matter what that number is, its derivative is going to be 0. So now to solve for dy dx, so now it's algebra. So I subtract. So this didn't have a dy dx in it. So I move it to the other side, and then I divide by whatever's in front of the dy dx. In this case, 2y. So now when I divide by 2y, the 2's are going to cancel, and so I get negative x over y. Okay, now that's the derivative at any point. Okay, but I wasn't asked to find the derivative at any point. I was asked to find the derivative or slope of the tangent at the point 3, 4. So now I plug in 3 for x and 4 for y, and so I'll get negative 3/4. So that's the slope of the tangent. Okay? Now, let's say I wanted to take it one step further. Okay? And I wanted the equation of the tangent. Okay? So remember, to use the point slope formula is y minus the y value equals m, the slope, times x minus the x value. And so this is, okay, okay. Whoops. Okay, so let's be clear here. So this is the slope of the tangent at any point. Slope of the tangent at any point on the circle. Okay? This is the slope at that point. At negative 3/4, we get the slope is negative 3/4. Then this is the equation of the tangent line. Okay, so here it just says find the slope of the circle. Okay, I want you to go ahead and do, I want you to find the slope of the tangent at any point, the slope of the tangent at the given value for x, and then I want you to find the equation of the tangent line for practice 2. right, so Joey, what is the slope at any point for that circle?
Negative x over y.
Negative x over y. So it's the same thing as the last one, because the only thing that was different is the point and the radius. But negative x over y. So everybody okay with that? All right. All right, so Rhett, if I want to know the slope at x equals 6, I also need to figure out the y that goes with it. So what's the y when x equals 6?
Root 13.
Okay. Whoop. Okay, so radical 13. Good. All right, so then...
How did you get that?
How did you get that, Rhett?
You plug it into like the original equation.
So the original equation. So 6 squared is 36. So 36 plus y squared is 49. So y squared is 13. So y would be... Actually, could you have plus or minus? You actually could, because there would be 2 points on the circle. Okay? So 2 points on the circle. But let's use the 6 radical 13, since that's the one that Rhett came up with. So Rhett, what would be the slope at that point?
Negative 6 over root 13.
Okay. All right. So everybody okay with that? All right, so Joey, what would be the equation of the tangent at that point?
I do not know.
Okay, so you use the point slope formula. So it's y minus the y value equals m times x minus the x value. So y minus y sub 1. So y minus radical 13 equals the m that we just came up with times x minus the x value. Okay, that's the point slope formula. All right.
Mr. Strong,
Yes.
would it be plus x plus 6 because it's a negative 6 originally?
Was it a negative 6?
Yes.
Oh no, it wasn't.
No,
Never
it's
mind.
only a
Never mind.
negative
I'm
6
thinking with the derivative equation.
Yeah. But let's see. I don't know if I don't want to confuse you here, but see at x equals 6. See, let's say this is at x equals 6 here. See, there's actually 2 points. It's plus or minus the radical. And so the slopes would be negative 6 over radical 13 and negative 6 over negative radical 13. So then that would be a plus on, so we change that. But anyway, I don't mean to make it harder than it has to be. So anyway, any other questions on that? All right, so maybe what we'll do is just put at 6 radical 13. Okay.
Mr. Strong,
Yes.
could you go back to that equation just real quick?
Sure.
Thank you.
So the blue here is the point slope formula, and you're just plugging in 6 for the x1, radical 13 for the y1, and then your m is negative 6 over radical 13.
So for your final answer, would you multiply out the negative 6 over 13 or radical 13?
You could. If the answer says that they want it in slope-intercept form, then that's what you would do. Okay. But if it just says write an equation, that's good enough. Okay? All right, any other question? I appreciate those questions. Okay? Whoops. So annoying. Okay, so notice that the derivative of an implicit function involves both x and y, not just the independent variable x. Because with implicit, you really don't know which one is the independent and which one's the dependent. Now, these can get a little tricky, okay? And this is where, like, you're going to want to put in the dx type stuff. So just kind of watch this one. So here I'm taking the derivative, and I say, okay, the derivative of y squared, we did that. That's 2y dy dx. The derivative of x squared is 2x dx dx. But now the derivative of sine xy, see, that's going to be cosine xy times the derivative of the inside part. Well, the derivative of the inside part using the chain rule, I have to use the product rule inside the chain rule. Okay? So, let's go through it again. So, the derivative of y squared is 2y dy dx equals. The derivative of x squared is 2x dx dx. The derivative of sine blob is cosine blob. But then to multiply by the derivative of the inside part, the derivative of xy is x times 1 dy dx plus 1 dx dx times y. So I'm going to just tell you that's really easy to lose one of those dy dx's or dx dx's. And that's why I write them in. Okay? Now, okay, so the calculus is done, but the algebra is getting more vicious here. All right? So, first of all, if we clean up our dx dx, so we have 2y dy dx equals 2x, so the dx dx cancels, plus cosine xy, and then x times 1 is just x dy dx, plus, and then I went ahead and distributed this through. So, cosine xy times x dy dx plus cosine xy, and then all this just simplifies to y. All right, now I have a little bit of an algebra problem here, okay? What's the algebra problem that I'm faced with here?
Really quick, Mr. Strong.
Okay.
There's 2 cosines in that second level. Where did the second cosine from?
We distributed through here. So cosine times x dy dx and cosine times y. Okay? So it's just distributed. All right, so what's my algebra problem now? It's not a calculus problem, but it's an algebra problem. And you're going to be faced with this more often than not. Okay? Here's the problem, is that we're trying to solve for dy dx. Okay, you might say, oh, just do like we did on the last one, just divide everything by 2y. The problem is I have a dy dx over here too. And so you can't solve for dy dx in terms of dy dx. That's no good. That's like solving for x in terms of x. Can't do it. So what you do is you get the terms that all have dy dx on one side and the terms that don't have dy dx on the other side. Okay? So this I'm just leaving alone. This I'm just leaving alone. But this has a dy dx. So this whole term, I'm going to subtract it from this side. So I'm going to put it over here. So 2y dy dx minus x cosine xy dy dx equals 2x. And then this did not have a dy dx, so I just left it alone. Well, I put the y in front. Okay? Now, again, the goal is to solve for dy dx. So algebraically, what I need to do is factor out a dy dx. So I factor out a dy dx, the thing I'm trying to solve for, and I'm left with 2y from this term and x cosine xy from that term. Okay, I do nothing to this side. All right, now, whatever I have in parentheses now, I divide both sides by that. So 2y minus x cosine x, because all that will go away. And so then I divide this side. And so, believe it or not, that's the answer. Okay? So that's the answer. It's getting pretty messy. You got x's and y's in there, but that's the derivative. So 2x plus x cosine xy divided by 2y minus x cosine xy. Okay? So let's see how you can do. Let's see if you can do one of these more complicated ones. So I'll leave this up. You try practice 3 on your paper. All right, so Jordan, when you've got it.
Alright, so I got dy over dx equals negative x squared plus 3x minus y squared plus 3y. That's with factoring the y out, or the 3 out. And, oh wait, that I did not get that.
So it's like you have your 3x and 3y switched. So let's go through it, or at least as much as we can here. So first, the derivative of x cubed is 3x squared dx dx. Minus the derivative, or plus, the derivative of y cubed is 3y squared dy dx. Okay, now to do the derivative of negative 9xy, you have to use the product rule. So here we're doing the negative 9x times the derivative of y, which is 1 dy dx. Then minus the derivative of negative 9x is negative 9 dx dx times y. Then you get the dy dx terms together. So that would be the 3y squared dy dx minus 9x dy dx. All the terms that don't have a dy dx, move them to the other side. And then you factor out the dy dx and then divide by what you have in parentheses. So here, if you had this, Jordan, or something close, what we did here to go from here to here is factor out a 3 in both the numerator and the denominator, and then it'll cancel. The 3's will cancel.
I messed up with the product rule. I forgot you had to do the dy dx up there too.
Yes.
So that's where I messed up.
Okay. So anytime